All right. If there is no question about what we covered before, and uh, everything is relatively clear up so far, I'm going to start talking about what I would call the closest we get to solid mechanics, at least within the scope of this course. Now, the way I want to start this is, remember that when I talked about a vibrating system, I said any vibrating system, right? Any, and I say it as a general statement, that has three elements. Right? One element is the element that stores kinetic energy, which I said it can be a mass or inertia. One element can store potential energy. I mentioned spring, that we saw a spring, and I also mentioned elasticity, but I didn't really explain what elasticity is, and it's going to be the topic for today's course. And an element that dissipates the energy. For now, just put that aside. We're going to simplify our systems, assuming that there is no damping. That helps us to clarify what we want to cover or what we want to talk about. Now, as mechanical engineers, obviously, we do not always deal with systems with spring and mass. Right? We do have those systems, right? Very common, I would say, when you look at the car chassis, or we have a shock absorber somewhere when you're installing, to make sure that whatever system you have is safe from any sudden impact or shock or vibration. So we typically use a spring with combination with a damper. We do have simplest, like other systems. For instance, if you think about your uh, like old-fashioned watches, right? They have springs in them, obviously. But more generally, when we look at structures like in mechanical engineering, we do deal with solids a lot, right? Think about solid mechanics course that you had that course before. When you look at a beam, you were looking at beams, you were looking at different parts of a structure, from bolts to uh, plates to anything that you use to put together a mechanical system. Right? A lot of those parts are not actually springs or dampers. They are just solid parts. So, following the statement I made that any system, any oscillating system, obviously a lot of those solid systems made of solid parts, uh, they are also under vibrations, right? There are forces applied to them from outside or the outside environment, and they oscillate, they vibrate. A very good example is the body of your car. Right? It obviously oscillates. How do we deal with those systems? Now, since we learned spring mass system and how do we deal with it, we have a way to find the equivalent of those systems, those systems made of solid parts. We have a way to find the equivalent for those systems, which can be very similar to just the spring mass system, or later on you will see spring mass damper system. Think back when we were talking about, I'll put this under stiffness. Think back when we were talking about spring. I defined the spring. I said, well, pretty much the spring is a mechanical link that connects two parts, connects two masses to parts of a system. And in that link, right, we said, well, we define the stiffness as the relationship between the force that is applied to that link. Right, I have my spring here. We define the stiffness as the relationship between the force applied to that spring and the amount that the spring is deformed. Whether it's stretched or compressed, it depends how the force is applied and whether our spring can handle compression or extension, or both. So I'm just going to put it here. In a spring, we defined stiffness as K. Let's put it this way. We show the stiffness with K, right? Spring constant with spring stiffness as force. Let's just do it the way that is more familiar. We said F over X, X being the deformation in the spring. So pretty much what we said, well, this is force or load on the spring divided by, as I said, deformation. Now we can use this similar logic, for other systems. Right? We have, I'll call it spring-like behavior. When we have longitudinal deformation or transverse deformation or even torsional deformation, we are applying some force. Think back about solid mechanics. Right? Where you were measuring the bending in a beam. Right? You had a beam, you're applying your force, right? You're measuring how much this beam bends. Right? In that case, also you have a force applied and you have a deformation in that beam. So you still have a spring-like behavior. Right? It's behavior similar to spring. Another example would be when you were looking at the force applied to a bar or rod. Remember, again, in solid mechanics, one of the first things that you learn, how to find the relationship between the force applied to a bar or a rod and how much that bar is deformed. So these spring-like behaviors actually help us to find the equivalent of such systems. Right? So all we need to do in those cases is that we have to find the relationship between the force and deformation, like that fraction that I put there. Once we know that fraction, force or load over the deformation, that ratio is going to give us a stiffness. And we can say, well, I can look at this specific beam under this load at this point and say, this is a spring mass system pretty much, or this is just a spring, because when I apply the force, it deforms. As long as I know the stiffness value, K, I can look at it as a spring. So I'm going to classify possible cases that we already know from solid mechanics, and we can talk about them into three cases. I'll talk about longitudinal deformation, which is pretty much very familiar again from solid mechanics, transverse deformation, and torsional deformation. So start with first one. Let's say case one, and I'll call it, let's use a different color. I'll call it longitudinal deformation. Now think back in solid mechanics. We were looking at, let's say, a bar like this. Hopefully that reminds you of the whole problem in solid mechanics that we're looking at. We said the force F is applied to this bar. Let's say the length of this bar is L. L is the length of the bar, and I know the area, cross-section area, or cross-sectional area. This is a solid, could be a rod, could be a bar with a rectangular cross-section area. And E is modulus of elasticity. Elasticity. The units can be meter area, meter squared, module of elasticity, Pascal, gigapascal, kilopascal. Now, hopefully you remember that, well, when we apply this force, in this case, let's say I'm pulling it, right? Tension force. Well, we're going to see some change in length, right? Depending on what material it's made of, that change can be a lot or can be small, depending on how strong or how stiff this material is, depending on what the modulus of elasticity is. Now, when we were dealing with this, we found the relationship between this deformation and the force. Can someone tell me, do you remember what that relationship was, given we know the length, cross-section area, and modulus of elasticity? Yeah, it's old knowledge, huh? Delta, hopefully you remember this, was the amount of deformation in this bar, whether it's increasing the length or we are compressing it and the length is decreased, was FL over AE. That was the amount of deformation. Tell me if you don't remember this or you haven't seen this. You should have seen this in solid mechanics. Now look what we got. We already have a relationship. As I said, all I need to do is to find the relationship between force and deformation. So we already have it. If I move things around, F is equal to AE over L delta. This is my force or load. This is my deformation. So what does that mean? That means whatever is connecting these two, connecting the force to deformation, is going to be my stiffness. So this becomes my stiffness. Very similar to spring. In spring, we had F equals to Kx. Now we have F is equal to AE over L as the stiffness multiplied by deformation, which is delta. So in this case, K are called K equivalent because this the stiffness for the equivalent system becomes AE over L. What does that mean? It means that when this bar is under a longitudinal deformation, some force is pulling it or compressing it, I can easily just say this bar is pretty much as a spring this is F, same F as applied to the bar, is a spring with this stiffness K equivalent. See, so pretty much I replaced, let me put this, I replaced the bar or the beam under tension, could be compression, with a spring. Now, if I had a mass attached to the tip of this beam, keep in mind that I ignored the mass of the beam. Sometimes what we do is that we say, well, let's assume the whole mass of the beam is concentrated at the tip of the beam or somewhere else. But in this case, let's just say we ignore the mass of the beam. Now, if I had a mass attached to the tip of this beam, this could be a spring mass system easily. Right? If I had the beam like this, and I had a mass at the tip, and I was applying this force there, this could be easily a spring mass system, right? And this is K equivalent. You don't even need to put the force there. There you go. Then you can use whatever we know from before for a spring mass system to study this system. If they have something that is under oscillation, some force or some initial conditions are applied to this beam along its longitudinal axis, and it oscillates. Keep in mind, when we talk about oscillation in solids or solid materials, we're talking about very, very tiny amount of change in length. or a very tiny amount of deformation. So whatever we know from a spring mass system, now we can use to study this beam under longitudinal force. So that's case one. It's one case that you hopefully remember from solid mechanics. That's how we find the equivalent of this system, if you want to look at its oscillation. Now, we also had transverse deformation. We had a beam. We were studying how much it is deformed, like the shape of this curve. We could find the deformation at any given point when we had the force. Remember, we were drawing shear force diagram and moment diagram, and then we were using those to find the bending. The bending in the beam pretty much is deformation, how much is deformed under force. Now, in the second case, I'm going to look at transverse deformation. Deformation is like this, that the force is applied not in the same direction as the deformation happens, like it's perpendicular to the direction of the main axis of my beam. Let's take a look at that. So all that we're doing here is we are generalizing what we learned. As I said, just because we talk about the spring mass system or spring mass damper system, it doesn't mean that they limit us to use those results for a spring mass system. Now we can see we can use the same results to study structures. So I'll call this transverse deformation. I can write a better transverse than that. Transverse I'm going to talk about multiple cases because we saw multiple cases in solid mechanics, right? When we were talking about beams, the reason we're talking about beams because beams are probably the most common types of elements that can be used to study different types of structures, even complicated ones. Pretty much you can always assume that they are formed by multiple beams, right? I'll talk about a beam. Well, I'll talk about different boundary conditions that we had, specifically 3 of them now. A cantilever beam, right? We had a cantilever beam that one side was clamped, the other side could move. We talk about a beam, a simply supported beam on both sides, and we'll talk about clamped beam. Right? We'll see how can we find the equivalent to those systems. So let's talk about cantilever beam. Now in a cantilever beam, we have something like this, let's say, and it's clamped on one side. And let's say a force is applied here. The beam has a length of L, the same story. Now in this case, I need something else. So I'll give you A as, you actually don't need A. I'll give you E as modulus of elasticity. That's whatever material this beam is made of. And I as area moment of inertia. Moment of inertia of the cross section, right? This is for area, so of the cross section of this beam. What do I mean? Oh, this beam has some, I'm looking at it from one side, right? So it has some cross section. I'll draw it here. I'll exaggerate so it's bigger, we can see This is the cross section of this beam. This I is the area moment of inertia of the cross section. Now, do you remember what was the deflection when we were applying a force on a cantilever beam on its tip? Do you remember what was this deflection? As I said, all we need to do is to find the relationship between the deformation and the force. Right? Then we get the spring-like behavior, and we can use that to find the equivalent of the system. Can anyone tell me, again, I understand, long time ago, any guess about what was this relationship? Given a force applied to the tip of a cantilever beam, how much that beam is going to deform at the tip? Yeah, I know, long time ago. I wouldn't have remembered that either, probably, if I didn't know I'm going to talk about this today.
Is it y is equal to mx squared over 2ei?
Mx squared over 2ei. No, I actually don't know what the relationship is. Maybe it's for a specific kind of configuration of the beam, but not in the, for a cantilever beam and the force applied at the tip. Now, x, I'm guessing by x you mean the distance from the tip, right? This direction. So what was the denominator of what you said? You said m. Oh, you're talking about m, which is, by m you mean bending, I'm guessing. You probably had some relationship between how far you are from this end, x, and where the force is applied to get the amount of deflection in the beam. But let's just talk about this specific case, which is L, right? The force is applied at the end of at the tip of this cantilever beam. So this x is pretty much L amount away from the from where the beam is attached to fixed support. Now in this case, I'll give you the equation. Delta, or deformation, was F L to 3 over 3 I think. E being the modulus of elasticity, depending on what that beam is made of, I is the area moment of inertia of the cross section, L is the length of the beam, F is the force. Remember, this delta is the amount of deformation at the tip of the beam. If I wanted to know the deformation at any given point, this should have been written as a function of x. Now again, I have a relationship between force and deformation. Right? F is equal to 3ei over L to 3 delta. This is my force. This is my deformation. As a result, this is my stiffness. So this means that the equivalent of a stiffness for this case would be 3ei over L to 3. Now, I'm going to say this, and I emphasize that, but I believe that still there are going to be mistakes when I see at your works later on. That's how much I trust you guys listening or remembering what I say. This I is the area moment of inertia of the cross section, but remember the direction. We have the force applied in this direction, right? Vertical direction, and the bending occurs this way. So all I care about is the area moment of inertia around this horizontal axis. If this being the exact area of the cross section. What I care about is I about this axis, this horizontal axis. Because the bending is happening in this way. If this is B, this is H, can someone tell me what is the area moment of inertia for this cross section? You remember that from solid mechanics. What would be the I for this case? That's fine if you don't remember. I'm just curious if someone remembers that relationship. Given the width and the height of the beam, what was the area moment of inertia for this area?
Is it rectangle or round?
Ask again. Sorry.
Is it a rectangle or round?
It's rectangle. So the width is B, the height is H.
H to the third power over 12?
Exactly. Thank you, Yusuf. So B H to the third over 12. So given any cross section, you already know from solid mechanics how to find the area moment of inertia. So that you can find. E is a marginal of elasticity that for any material you can look it up, right? Just usually given. So we can easily replace this system with a spring. Let me just put it right in front. So that would be the equivalent is a spring and the force is applied here. Stiffness of a spring being K equivalent. Keep in mind, I'm going to emphasize this. This is the equivalent of this system as long as we have a force applied to the tip and we are modeling the deformation at the tip of the beam. Right? So what I'm doing is that I'm replacing that deformation at the tip of the beam with this spring system. So if I had a mass attached to the tip of the beam, there would have been a mass attached to this spring system, and I had a spring mass system. I'm going to show you an example later on about this case. So the whole system cannot be modeled as a spring with this stiffness. The system, or better to say, a cantilever beam with a force applied to the tip, and the type of system we're looking at, deformation on that tip, can be modeled using this approach. If we were looking at deformation in any other point, the stiffness would have been different. So that one was a cantilever beam. Let's look at simply supported beam. Simply supported beam. We saw that also in solid mechanics. I have a beam like this, simply supported. So here it is, and here it is. And I'm looking at a special case when the force is applied exactly in the middle. Again, the relationship between deformation and the force changes depending on where the force is applied. In this case, I'm just looking at the case where the force is applied exactly in the center. Now, if the force is applied in the center, we're going to have a deformed shape. I'm going to exaggerate, obviously. You don't see this much deformation. Well, unless it's a very soft material. This would be your delta. Now, the relationship between the force and deformation, that I doubt that you remember. I barely remember it. But I mean, I guess I have to correct myself. Just because I barely remembered, it doesn't mean that you don't remember. L would be the length of the whole beam, right? We still have E as modulus of elasticity and I as the area moment of inertia of the cross section. Keep in mind. So the cross section could be a rectangle, could be a circle. In this case, I'll just put the some rectangle there. Now delta, or where to say I put it, I start from what I did before. F, no, I start from delta and then I move things around. So delta would be F L to 3 48 EI. So I can move things around, the same story, 48 EI over L to 3 delta. The relationship between force and deformation, so this becomes my stiffness. So K equivalent, where do I put it? I put it here. K equivalent would be 48 EI over L to 3. This is my equivalent of stiffness for the system. Now, what does that mean? It means this system is equivalent to a spring like this with the stiffness of K equivalent. I want to remind you that we are modeling the deformation at the center of the beam when the force is applied exactly at the center. If the force was applied somewhere else and we're looking at deformation in another place, we needed to know the relationship between deformation and force. This delta equal to FL to 348 EI is for this specific case where the force is applied exactly in the center and delta is also exactly at the center. So if we had some kind of mass at the center, this would have been a spring mass system. Now we could study the vibration of this beam, oscillation of this beam at the center, as long as the initial conditions, some initial velocity or displacement would have been applied to exactly the center. Okay, so that was the second case. There's a third case I want to talk about, and that's clamped beam. Clamped beam. So the same story. I have a beam, not in this color. I have a beam. In this case, it's clamped on both sides. I'm looking at a special case when the force applied exactly in the center. And let's say I have some deformation. Maximum deformation happens in the center when the force is applied in the center. Both cases for clamped and simply supported. Now this is also the length is L. The area of cross section for this beam is also can be a rectangle or can be a circle, but all we need to know is we need to know the modulus of elasticity, or Young's modulus, or what material is made of, and we need to know what is the area so we can calculate the area moment of inertia, or I. Knowing those two, right, and keep in mind I is around about this axis. So knowing I and knowing E and knowing L, if this is force F, right, we can go about this by finding the relationship between deformation force. You may or may not have seen this in solid mechanics. Delta, deformation exactly the center, would be, I believe, FL to 3, 192 EI. I have to double check this. Let me see. Yes. So FL to 3, 192 EI. So moving things around, F is equal to 192 EI over L23 delta. Force, deformation, they are related using stiffness. So that would be the equivalent to stiffness for this system, right? 192 EI over L23. This means that if I have a clamp beam and the force is applied exactly at the center, or initial conditions are given at the center, right? I push it or I have an impact on the beam and the beam starts oscillating, which happens a lot in different structures. This can be modeled as a spring with the equivalent stiffness of 192 EI over L23. Like, this gives you a lot of power. Now you are not limited to just a bunch of spring mass systems. Now you can look at a lot of structures and see how can you study their vibrations or their oscillations. Let's take a look at an example before I talk about the last case, which is torsional vibration, and see how does this whole thing work. Right? I talked about longitudinal deformation and talked about transverse deformation. Now let's take a look at the example. This example says we have a 200 kilogram machine which is attached to the end of a cantilever beam. Right? A 200 kilogram machine is attached to the end of a cantilever beam of length. So we're given the length of the cantilever beam of length 2.5 meters. E, or modulus of elasticity, of 200 times 10 to 9 Newton meter squared, and I, or area moment of inertia, is given directly, is 1.8 times 10 to minus 6 M4. If you remember that from before. Now, it says assuming the mass of the beam is small, mass of the beam is small compared to the mass of the machine, so we can safely ignore the mass of this beam of the machine. What is the stiffness of the beam and what is the natural frequency of the system? Frequency of the system. So we have a cantilever beam like this. Some mass, some machine is attached to the end of it. This is probably the simplified problem for some machine somewhere sitting somewhere in a factory, let's say. We could model the attached structure, the way the machine is sitting on that specific area as a cantilever beam. So this is probably a simplified version of actual problem. And they want to know the natural frequency, because we'll see later on it really is important to make sure that when you design something, you stay away from natural frequency 90% of the times, to make sure that you don't have huge oscillations. We'll talk about it when we talk about force vibrations. So now this, we know properties of the beam, the length E and I, this mass is given 200 kilograms, and we want to know the stiffness. So it's a cantilever beam, mass is attached to it, right? This mass is going to be your load. Keep in mind, I told force or load. Now, in this case, there is no force. It's just a mass. So this is our load. This is our force, or better to say load. We have M, W would be mg. Let's just start with the stiffness. So the stiffness for a cantilever beam, or we're trying to replace this beam with a spring, right? What we want to do is we want to get into this. We want to have a spring and the mass attached to it. So what I want to do is that, well, what is the equivalent of the spring for this beam's cantilever beam when we are looking at the oscillation of the tip? This oscillation. Let's say it oscillates. If you want to imagine the oscillation, this oscillates like this. It goes from one end to the other end. Right? It goes like this. Not that much deformation, exaggerated. So equivalent of the stiffness would be 3ei over A, if I'm not wrong. Actually, you can look into cantilever beam. So 3ei over L to 3. Just replace the values. You're given everything pretty much you need, times I, which is 1.8 10 to minus 6, divided by the length is 2.5 to 3. That'll give you a value. Do I have the value? I did the math, so, but you definitely double check this number. Hopefully I got it right. Now, once you know the stiffness, well, there we go. What is the natural frequency of the system? Now you have the stiffness, you have the mass, right? Hopefully the rest is straightforward. The natural frequency would be the square root of a stiffness, in this case equivalent to a stiffness over mass. So 6.91 10 to, I can do it better. 6.91 10 to 4 divided by the mass. The mass is 200 kilograms. This one, I actually do not have the number. So one of you guys, if you have calculators, your calculator around, double check the first number and give me the number for the second one. If you don't, that's fine. You can always do this math. Whatever you get would be radian per second. So this is going to oscillate, and it oscillates with this natural frequency. Great, right? Now we can go from solid mechanics to an oscillating system. You will see later on when we study different properties of an oscillating system. Always keep in mind that when we talk about the spring mass or spring mass damper system, we are not just talking about the physical spring damper, a specific spring that just a spring like this. We are talking about any system. 18.58. Thank you, Chris. 18.50. Okay. 58, 6, same. Thank you, Zeri and Chris. I probably should put in parentheses here, coming from Christopher and Zeri. So if there's a mistake, I don't have to be held responsible for that. Okay, I trust you guys. You guys are much better than I am in this. So there it goes. Now let's talk about the third case. I talked about longitudinal deformation. I talked about transverse deformation. Let's talk about the third case that we did not really talk about that much, and it's torsional deformation. In order to talk about the torsional deformation, which is pretty common in mechanical engineering, if you think about shafts that we use pretty much in every single design, well, most of the design systems we design, most of those systems include shafts. Like if you go to a power plant, or you're designing a specific engine or generator or a set of gears, you all have, you know, shafts, and shafts rotate. Right? That rotation, you know, let's see if we can model that as a spring. Now, before I talk about torsional deformation, I have to generally tell you something about torsional springs. We only talked about case 4. No, it should be case 3. So I talked about, let's see, maybe I'm wrong. I talked case 1. Is that a part of case 3 too? No, this is, so I talked about case 1, which is longitudinal deformation. Case 2 is transverse deformation, which included cantilever beam, simply supported beam, and clamp beam. So this example, now I'm talking about case 3, which is torsional deformation. Yeah. So, torsional springs. We didn't talk about torsional springs. I only talked about linear springs, like springs over there to say springs like this, which are not the only type of springs. We have multiple or different types of springs when we're dealing with systems, mechanical systems or engineering systems. Now, another one that is, it could be, or better to say it's interesting to look at, is torsional spring. Now, I didn't talk about it because it's pretty much the same as a typical spring that we talk about, a torsional or compression, tension or compression spring. The only thing that changes is that in a typical spring, we had the relationship between force and deformation when we were applying tension or compression. And the relationship was, so I'm going to put it here, torsional spring. When we were talking about those kind of springs, like again, springs that can handle tension or compression, we said, well, F is equal to Kx. Right? Force is equal to K, the stiffness, multiplied by deformation, like in X direction. Or it can be Y direction, depending on which axis you use and what direction you're looking at. How do you choose your coordinate system? Now, in torsional spring, which a very good example of it would be the springs that you see in your old-fashioned watches or clocks. They had torsional springs, right? If you look at details or look at the inside system, you will see there are some springs that are like this. I'll try to draw it, something like this. It could be attached at the end somewhere. It's a pretty bad drawing. Let me give it another shot, at least make it a little more clear. And it's like fixed at some end. That's how we show torsional spring. Sorry. Now, good example would be the springs you see in a wristwatch or in a clock. They are there to, especially old-fashioned watches. Another example I can think about right now, maybe, I don't know, when I was a kid, there were these toys, the car toys, that they had kind of torsional spring inside. The way, at least I used to play with them, was we could push them or take them, just making sure that the wheels are in contact with the surface. We could take them all the way to the other side by applying a force. And when at least I remember that way, when I let it go, right, the car or the toy, would have been accelerating the opposite direction, So within those toys, those toy cars, there were torsional springs that when I was pushing it all the way to one end, this spring was compressed, right? And some potential energy was stored in the spring. And when I let it go, that potential energy stored in the torsional spring would have been released and would have created some acceleration in that toy car. Again, that's what I remember from my childhood. Maybe you haven't seen it or it doesn't exist anymore. I'm not that old, but you know, things change fast. So, torsional spring. The difference here is that instead of a relationship between force and deformation, linear deformation, now you have a relationship between torque and the angular deformation. We usually show the stiffness for these springs with KT, standing for torsional stiffness. So now you have torque instead of force and deformation, like linear deformation. You have torque and you have angular deformation. And this is in radians now instead of meter. Torque in this case would be Newton meter. Right? You find the unit for KT. Now, hopefully that makes sense. It's very similar to what we had for a spring, but in this case it's torsional. It's practical because, again, in mechanical engineering, we do deal with, I'll keep this as a side note. Keep in mind everything I said about the springs. Torsional springs could be also in series, in parallel. We can add them up. You can put them together to get the specific stiffness that you want. So whether they're in parallel or in series. We also have torsional dampers that we're not going to talk about it, but pretty much similar idea. A damper that damps the motion in torsional direction. Again, it's not a topic for this, and I may or may not mention that, but just, there are also torsional dampers. So, going from torsional spring to torsional deformation. Now, if we have a system that is under some moment, under some torque, which happens a lot, again, in mechanical engineering. Think about a shaft like this. You've seen this in solid mechanics. Like under some torsion. Let me put it here. Or torque. Hopefully you remember when we were looking at the cross section, very brief. We were looking at the cross section. We said there's going to be some deformation, right, because of this torque. Let me do it this way. This torque is applied. Let's say this is the torque. There's going to be some deformation. Right? Seen this. And we said if I call this angle deformation, I guess in solid mechanics we were calling it phi. I'm just going to use theta here. So the shaft is under torque. It's applied. The torque, some torque is applied to it. Some deformation, angular deformation happens in that shaft. I show it with, I represent it with theta. Does anyone remember what was the relationship between the angle of twist? We're calling this angle of twist, probably. You've heard that way. If this, what was the relationship between this angle of twist and the torque applied to this shaft? Let's say we also know the length of the shaft is L. What else I know? I know the G, which is shear modulus of elasticity, or modulus of elasticity for shear, modulus of elasticity. And since this is circular, let's say J is the polar moment of inertia.
Professor, is it TL over GG?
TL over JG, exactly. Was Dominic?
Yeah.
I do feel a little bit of pride right now, Dominic, because I remember we had solid mechanics together. So
I do remember that too.
Hopefully you remember it from there. I'm just giving
I
myself
do. I do.
credit. Okay. Yeah, probably have seen it later on a lot in machine designs. So hopefully everyone agrees with Dominic, right? The angle of twist is TL. Let me use the same L I used there. Same way I wrote T. TL over JG. And this one was the angle. I'm going to use the same thing so you've seen twist. And this is the torque applied to the system. All right. Now, following what I said about the torsional spring, which I said is the same story, the relationship between force and deformation, now we need to find the relationship between torque and angular deformation. If I do that, obviously I can rewrite this as T is equal to JG over L theta, and this becomes my stiffness. So now, any shafts, any system under torsion, as long as you can find the polar moment of inertia, remember the polar was, hopefully you remember that. For instance, for let me see if you remember that a little bit. If I have a circular cross section, does anyone know? Let me give you some, I guess, properties for that. What should I give you? Let's give it the diameter. If the diameter of this cross section is D, does anyone remember what was the polar moment of inertia for this?
I think it was pi d to the fourth power over 16.
Very close. When we have the diameter, we say pi over D to 4 over 32. But yes, that's very close. Unless I'm wrong. Pi D to 4 over 32. So as long as you know this moment, polar moment, and you know the shear modulus of elasticity, you're good to go, right? You can find, or you can model this as a spring mass system, or as a spring. The shaft, you can model the shaft as a spring. Now, let's take it a little further. What if we have a hollow shaft? What if we have something like this? I barely remember this, but you guys probably deal with it more often than I do. So let's just make sure that it's there. If I have a hollow shaft and I call this DI, and let's call the diameter of the outer part DO, what is the polar moment for this?
Isn't it pi over 32 d outer to the fourth minus d inner to the fourth?
Exactly. Thank you. So D outer to fourth minus D inner to fourth. So any shaft you see, and you know you can find the polar moment of inertia, you may or may not have seen it in solid mechanics, that for any other cross section, it's not just circular cross section. So as mechanical engineers, we deal with circular cross sections way more often than any other type of cross section. So that's what we typically know without even looking at some table or looking it up somewhere. So you know the polar moment for the cross section, you know the torque applied to this shaft, so it tells you how much is the angle of twist or how much it is deformed in angular direction. Pretty much you can model that as a torsional spring. So what you get is that, well, the equivalent of this system, the equivalent of this shaft, it's a very ugly shape, would be a torsional spring with KT equivalent, and this KT equivalent for your system would be JG over L. So any vibrating shaft, we can look at it this way. We can just replace it with some torsional spring and then again use whatever we found before. Keep in mind, all you need to do in the system response we found, X, right? You can just replace F with T and replace the stiffness with torsional stiffness. You can call it torsional stiffness if you want. But typically we just call it spring stiffness for a torsional spring. Hopefully that makes sense. Now, to get a better sense of it, I will highly encourage you to look at this example in your book. Look at, let me write it here. Look at example, I think, let me double check. I think it's 1.5.2, but doesn't hurt to check. Yes, it's 1.5.2. It's not about the torsional system, but it's a good example to show how can you even model an airplane's wing, right, as a cantilever beam, a very simplified version, and use what we found to find how its natural frequency changes. So example 1.5.2. 1.5.2 book. Take a look at that example. Hopefully it makes sense. It's talking about how can the natural frequency change as well. It gives you the wing of an airplane, and it shows how can it be simplified as a cantilever beam. It's a wing with, and in that example, I believe it's trying to say that the tank that keeps the fuel for the airplane is attached to the wing, and it can be filled or it can be empty, and you will see the natural frequency of the wing changes depending on whether the tank is filled or it's empty, or how full the tank is, which is an interesting problem because one of the situations that you look at the vibration is the vibration in the wing. You've all taken or most of you have been in a plane before. You've seen when you are flying somewhere in a plane, if you were close to the wing, you've seen how much the tip of the wing oscillates, right? If there is a turbulence, you will see a lot of oscillation in the wing. Personally, when I was a kid, I was always scared seeing that much deformation in the tip of the wing, because I was always thinking that this is going to break now. This is going to break. But even now, although I know it's pretty stable, I don't feel comfortable looking at the wing oscillating when I take a flight. So that's the situation that you have vibration, right? And the kind of vibration that they try to mitigate or damp that vibration in different methods, using materials that can absorb the vibration, or different ways that they can take that vibration and or take that energy out of that system, so make the vibration in the wing less severe. Obviously, if it is severe, you're going to have fatigue, and that's going to be a big problem. But anyway, that problem is giving you a simplified version of way of looking at an airplane's wing as a cantilever beam, and how can you actually use what we just said about the cantilever beam modeling or finding the equivalent system to look at its natural frequency and how it oscillates. Okay, so just to recap, I talked about how can we look at the systems that we are more familiar with instead of spring mass systems, systems that we've seen before, deformation in beams in different directions, in shafts, and how can we model those as vibrating systems, spring mass systems that we learned before. So now you see that from that simple spring mass system we looked at, and you might have thought that, what is this? When am I going to use this? I've barely seen it. Now you see, actually you see it everywhere, as long as we can convert or efficiently convert the system that you're looking at into a spring mass system or a spring mass damper system. Hopefully that helps give you a broader view of why did I say at the beginning of this course that everything in life is vibration and oscillation. That's an example of some of those things that you'll see.